This tutorial is entitled AC Analysis. However, in parentheses, I have put the name frequency response because, in a sense, the term frequency response perhaps better indicates the situation that occurs with this type of analysis. Often, the term AC analysis tends to imply a single frequency. But what will be done here is to vary the frequency and show the output as a function of frequency, both the amplitude and phase. So I use the term frequency response, and I'll probably refer to it that way as we go along, but the official title is AC Analysis. Now, we have the source here. There is a 10-volt peak. I made it 10 volts deliberately to make a point, and it's showing 1 kilohertz. However, when you run a frequency response, or AC analysis as it's called, the parameters that we will set in the AC analysis window override what you have here. So the 10 and the 1 are totally immaterial for AC analysis. They would be appropriate certainly for transit analysis, but not for AC or frequency response analysis. If you need to have something other than 1 volt, and by the way, 1 volt is the default value if you do nothing else, but you can actually go into the signal source here, and where it says AC analysis magnitude, you can change that from 1 to any other value if you so desire. For example, with a doubly terminated filter with equal resistance on each end, it's often convenient to make that 2 so that you overcome the flat loss at all frequencies of 6 dB. Anyway, we'll leave it at the 1. And again, even though this says 10, it's going to show 1 as far as the frequency response is concerned. And the 1 kilohertz does not mean anything for frequency response. So how do we do the frequency response, or as it's called, AC analysis? We go up here and click on this, and we click on AC analysis. Well, this window comes open, and it initially comes out for the second one. It's easy to overlook this, but it comes out as gigahertz. The first one in hertz, I don't even think that's the default value. I think it's something I left earlier, but what you initially get is an extremely broad frequency range, one that you would never probably use in a practical application. In fact, this circuit would be totally invalid at 10 gigahertz anyway. Let me say this: the circuit was designed for a 3 dB frequency of 1 kilohertz. So I'm going to run it from 1/10 of 1 kilohertz to 10 times 1 kilohertz. So I need to change this to kilohertz. Okay, it's 100 hertz to 10 kilohertz. And for a wide frequency range, this is what we call 2 decades. From 100 to 1 kilohertz is 1 decade. From 1 kilohertz to 10 kilohertz is another decade. For a broad decade type sweep, it's better to use a decade type sweep. You have some other sweeps here. You have an octave sweep. An octave sweep is where you double every time you actually change in factors of 2. You go 2, 4, 6, 2, 4, 8, 16, so forth. A linear sweep is very convenient when you're working with a narrow bandpass filter around the narrow range of the filter characteristic. But we're going to stay with decade on this one. And I want more than 10 points. I'm going to change that to 100 points per decade as it reads here. When you go to linear, I think it's the total, well, when you have a decade sweep here, it's going to be points per decade. I think if you make that linear, well, that's the total number of points. I was correct on that. So let's go back to the decade and have 100 points per decade. And let's start with a vertical scale, and let's see what our output is. The output is Vout. It was left in there before. I always forget to sometimes with a new circuit to click on that one, but It'll tell you if you make a mistake. It's V out, and we hit simulate. Well, I'm going to go to a light background in this particular case. Okay, we have the amplitude response up here, and we have the phase response down here. Now we can put a grid on each. You select this one, I'll put a grid on it. And I could be interested in some applications with the phase shift, but in this particular case, it's a simple one-pole low-pass filter, so it turns out to be minus 45 degrees at the 3 dB frequency of 1 kilohertz. So I don't really need to look at the phase anymore. I'm going to kind of get rid of that. I've selected it. The red pointer over here tells me that's the one that I have selected. So I'm going to go up here and edit, and I'm going to delete that graph. And now this puts the entire screen for the amplitude response. And you can see on the linear vertical scale that as the frequency goes up, it starts out with a ratio of 1. That's at DC, or near DC. It's really 100 hertz. You never get to DC on a logarithmic scale. At 100 hertz, for most practical purposes, there is no attenuation in the filter, and so the output, the ratio of the output to the input, is simply 1, or almost 1, just a very slight difference there. And as you approach the 3 dB frequency of 1 kilohertz, it's down to 0.707, and then it goes on down to 100 millivolts at 10 kilohertz. Now, if this were a much higher order filter, which I'll have some examples later to demonstrate higher order filters, you would see that by the time you got up to here, you would be way down on a linear scale. It is much more customary to use a decibel scale for the vertical scale. So I'm going to go back and run this again. It's the AC analysis, leaving 100 points per decade, but this time I'm going to change the vertical scale to decibel and hit simulate. And now, once again, I have to kind of get rid of this one, so I'll click on it and go up here to edit, delete that graph, and then I want to change the background color again. It's okay. Now, in this case, I won't get the cursors out. We could get the cursors out and do some measurement, but you would find that this is at minus 3.01 dB at 1 kilohertz, or what we say the 3 dB down frequency. And higher frequencies roll on off, so to speak. This one pole low pass gives a roll off rate of minus 6 dB per octave, meaning every time you double the frequency, you go down 6 dB, or at least you approach the asymptotic behavior. Right in the region just above cutoff, it's a so-called cutoff, not really a sharp cutoff. You don't really get that effect there, but as you move farther on out, you really do get that effect. Some people would call this a Bode plot, because Bode plot techniques would actually give you a graphical approximation for this. And if you use a graphical approximation, you would use a straight line over till you get to 1 kilohertz and then roll down at minus 6 dB per octave or minus 20 dB per decade for one pole. And in fact, it's down at minus 20 dB at a frequency of 10 kilohertz. So what you have here, if you were to put a sine wave in that, let's say, has 100 hertz frequency, you would get almost the same output as you put in, a very, very slight difference in amplitude. If you put in a sine wave at 1 kilohertz with 1 volt, the peak value of the output would be 0.707 volts. That is after you reach steady state. There's always that transient behavior, as you've seen. But if you go up to 10 kilohertz, it would be down to 20 dB, and 20 dB corresponds to 0.1, so for 1 volt in, you would only have 0.1 volt amplitude at the output. Now again, this illustrates only a very simple low-pass filter. It's not really that sharp. You could only use this in applications where you've got some really high frequency stuff that you want to get rid of, and the one pole might be adequate for filtering and certain types of filtering and so forth. But if you really want a sharp filter, you have to go to more poles, a combination of R's and L's and C's, or with active filters, active devices, and R's and C's. So this should illustrate the idea involved in a low-pass or frequency response characteristic. I think I have time to just do one more quick run here. I'm going to show one more thing, and that is to go out 2 decades. Let's go back to AC analysis, and this time we started 100. I want to go to, well, actually this was 10 kilohertz. I want to go to 100 kilohertz. So let's do that real quickly and get rid of the second one down here. Edit, delete graph, and now you see it going all the way down to 40 dB down, minus 40 dB. We could also change the background again. We find it here. There we go. So we get down to 40 dB. 40 dB corresponds to 1% of the output, 1% of the input at the output. So for a signal source at 100 kilohertz, if it's 1 volt in, you would only get 10 millivolts out at 100 kilohertz. So that concludes the AC analysis tutorial.